Chapter 3. The Hubble Constant as Gravitational Redshift. The Schwarzschild radius equation defines the radius of an object with a gravitational potential equal to negative c squared divided by 2. These objects are considered black holes because of their escape velocity equals the speed of light. However, gravitational potential and escape velocity are observer dependent in general relativity, meaning there is a bit of tension between the Schwarzschild radius and the principle of general covariance. The resolution is that the Schwarzschild radius equation is an idealization that is only capable to approximate reality. This is an important and interesting thing to note, as many people are familiar with the Schwarzschild radius equation, but not everyone grasps the observer dependence of gravitational potential. Vacuum solutions like the Schwarzschild metric are idealized scenarios that place the observer at infinity. So it's not that the equation is inaccurate per se, it's just heavily contextualized. The point I want to make here is that an object with almost enough mass to become a black hole is already a black hole for some observers. For any given object, you can always describe a situation where some observer is unable to observe that object because of the relative geometry between the observer and that object. This means all objects are black holes according to some observer. Now, there are plenty of experts who would disagree with my language here. I don't really care. The entire concept of a black hole with a classical event horizon is dubious in the real physical world anyways. Placing an observer at infinity is silly and only confuses everyone.
We have considered black holes with evolving horizons, and necessarily we have given up the concept of an event horizon. Additionally, we have adopted the apparent and trapping horizon as a replacement.
All stars are embedded within the rest of the universe. The depth of a star's gravitational well depends on the observer's location with respect to that star. When the potential of the well equals negative c squared divided by 2, the star is unobservable. In figure 3.1, two observers are measuring the light emitted from a star embedded in a cloud of dust. Clearly, observer number 1 will measure more gravitational redshift in the starlight than observer number 2. That is to say, observer number 1 will measure a lower frequency in the starlight when compared to observer number 2. This is because the cloud contributes to the overall geometry as well. This is exactly why gravitational redshift can be aligned with Hubble's law. It is also exactly why the Hubble radius matches the Schwarzschild radius of the universe. It is not a coincidence. The two are inextricably connected. The Schwarzschild radius equation, RS equals 2gm divided by c squared, defines the radius at which an object of mass m generates a gravitational potential equal to negative c squared divided by 2. For any given mass, there is a corresponding Schwarzschild radius. For example, the Schwarzschild radius of 1 kilogram is 1.485 times 10 to the negative 27 meters, smaller than a proton. The sun's Schwarzschild radius is approximately 2.94 kilometers. If we plot the ratio of an object's physical radius to its Schwarzschild radius across all scales, a clear trend emerges. This ratio approaches 1 at the Hubble radius. Beyond that, the Schwarzschild radius becomes smaller than the actual radius of the object or system under consideration. The Schwarzschild horizon is determined by the distribution of mass and energy in spacetime. To make that link more obvious, we can express the Schwarzschild radius using the average mass density rho. This equation tells us the critical density required for mass distribution to form a Schwarzschild horizon. It sets the maximum allowable density for a given volume. This is a useful upper limit that scales with distance. For any value less than that limit, we can adjust the observer distance to recover whatever redshift we desire. Now consider a star observed at a distance of 1 megaparsec. To reproduce the Hubble constant through gravitational effects, the intervening volume must generate a gravitational potential equal to a Doppler recession velocity of around 72 meters or 72 kilometers per second. To find the required escape velocity, we calculate around 4.6 million meters per second. This corresponds to a uniform density of around 4 times 10 to the negative 23 kilograms per cubic meter, or 71,972 meters per second. This density is not sufficient to form a black hole, but it is enough to produce the same redshift predicted by Hubble's law at that distance. The Schwarzschild metric is useful for many applications. In this case, we have reinterpreted the cosmological principle so that isotropy is just a different term for spherical symmetry. We can plot the density required to produce Hubble's law alongside the density needed to produce a black hole. The two cross at the Hubble limit. To align with Hubble's law, we need a distribution equal to m of r equals 2 pi k r squared. For a star at a distance of r from the observer, the total mass within the volume having r is 2 pi times 0.833 kilograms per meter squared times the radius squared. The most common response to this claim is that there isn't enough mass to produce the Hubble constant. This retort is only made because stars are incorrectly considered to have an intrinsic gravitational potential and redshift factor. This is why I mentioned all that about black holes. The mainstream claims black holes have a fixed event horizon. But gravitational potential is a relative property, which means the total potential isn't determined until the moment of observation. This following graph is the most convincing of all. The red line represents all objects with a radius equal to their Schwarzschild radius, marking the upper limit of the mass-volume relationship. No object can exist above the solid red line according to general relativity. The blue rho is proportional to 1 over r, the green rho is proportional to 1 over r squared, and yellow lines, rho is proportional to 1 over r cubed, represent the range of all physically possible distributions of mass. No objects can exist below the solid yellow line. The dashed purple line is the nuclear density limit, which places an upper bound on the density of visible stars. The dashed gray line is the interstellar medium density floor, which represents a lower bound to the density of all celestial objects. All galaxies are between those two lines, and all physically realistic density profiles must exist within the shaded regions. The blue line is our density profile, arrived from interpreting the cosmological redshift as gravitational redshift. The density of individual objects was also plotted, such as proton, electron, and various cosmological objects. Almost all objects exist on our blue line.